All right. So today we'll play a little bit with the Ginzburg-Landau theory and try to see if we can calculate a couple of things about a superconductor. Okay, so let us start with yet another toy problem. Actually, it's not a toy problem. It could be actually a realistic problem, which is the critical current of a thin wire. So when I'm talking of a thin wire, I'm talking of a wire that has a diameter which is smaller than the coherence length. Now, as I have told you before, we'll start again. We have this thin wire. And we want to calculate its critical current. So first, of course, we have to start with an order parameter. And as I told you earlier, since the amplitude of the order parameter is much more difficult to apply a twist here, we can assume that the twist is actually on the theta. So in that case, the current of in the superconductor in the wire will be given by star by m psi mod squared Yes. Any question? Was there a question? Okay, if not, then this is E psi mod square Vs, which is nothing but our well-known expression ENV, if we know that Ns is psi mod square. Okay, now we need to calculate the critical current. That means that we have to write down the free energy and then minimize that free energy. So let the free energy density will be the free energy of the normal state plus alpha psi mod square plus beta by 2 psi to the psi mod to the power 1/4 plus, now I have to introduce the kinetic energy because I have a current. So a current means that I have a velocity, and if I have a velocity, then the Cooper pairs will have a kinetic energy. So half m star Vs square and multiplied by the density, which is psi mod square, plus if I have a current, if I pass a current, then I will of course produce a magnetic field. So I have to also take the magnetic field energy density. Alright. And this is what I will have to minimize. Now, first what I will show you is that this quantity I can make it all, I can assume it to be almost zero, and that is because half the kinetic energy term, half m star Vs square psi mod square is much greater than h square by 8 pi. So since this term is much larger than this term, I can actually neglect this term. Now, how do I show that? So let us first.
So can you say once again the reason for this claim?
Yeah, so that is what we'll have to prove. I'll prove it now.
Okay, sir.
Sir, why don't you write the Greensburg term?
Which one?
This Greensburg correction.
The Ginsburg term is here. This is the Ginsburg term.
It's much more generalized, I think.
This is the Ginsburg term because actually the Ginsburg term is coming from this. This Vs is coming from here. Clear?
Okay. Yes.
Okay, so first let us show that I can neglect this last term. So you know that if I have, let's say, a wire like this, then the magnetic field that is produced for a current I is H equals to, okay, when I'm proving this, I will go to SI unit. I'm sorry, I'm mixing units, but it doesn't matter. I just want to prove that this kinetic energy term is much larger than the field energy term. Now, I will put attention here that this I have done in SI. I was too lazy to convert everything in CGS again. Okay, so you know that the field energy is mu0 h square by 2 so that means mu0 by 8 pi square I square by r square. Correct me if I am wrong. Okay, the current I is the current density J into pi d square. D is the radius. I'm sorry, I have taken R here, so I have to take D for the radius, even though D normally stands for diameter. But remember that here D is the radius of the wire. Okay. So then this quantity will become mu 0 by 8 pi square r square into j square pi square into d to the power 4 pi square cancels. So therefore the magnetic energy, free energy is mu j square mu 0 by 8 into d square. Sorry, not by d square. D to the power 4 by r square. Yeah. So you can see that the maximum of this will decay as I go away from the wire, but the maximum value will be at the surface of the wire, and at the surface of the wire this will be of the order of this quantity will be of the order of d square. So therefore the magnetic term in the free energy is of the order of j square mu 0 by 8 d square. Let's calculate then the kinetic energy term. So this is half ns m star.
Sir, how these two radius are comparable?
Which one are comparable?
Are you just talking about the dimension of length, or
I am
basically?
talking of the maximum value. The maximum value is this. Then as you R increases, it will decrease further.
Okay. Okay.
Okay. So what I have to show is that the magnetic term is much smaller than the kinetic energy term. So I am showing that the maximum, that's why I am writing here what is the maximum value of the magnetic term. And if the
Right.
maximum value is much smaller than the kinetic energy term, then of course I am fine.
Okay, sir. I got that.
Okay. All right. So now again I know that J is NSAVS, or rather E star. If I am using star everywhere, I should use consistently. So Vs is J by Ns E star. So therefore, this quantity will become half of, sorry, Js m star divided by ns into star square. Now I know that from London's theory, I know that the penetration vector square is m star by mu 0 ns star square. So that means m star by ns is star squared. This is equal to mu 0 lambda square. So then F kinetic energy becomes half J square mu 0 lambda square. So now if you just compare these two terms here for Fm and F kinetic energy, can you mute yourself? Someone, I think there's some noise coming from someone. Yeah, I think it may be from Obro. Obro, can you mute yourself when you are not asking questions? Okay, so in the case of the magnetic energy, we had d squared, and in the case of kinetic energy, we have lambda squared. But I have already assumed to start with that d is much less than lambda. So therefore, the kinetic energy term is larger by a factor lambda by d whole square. All right. So we can legitimately set this last term to 0. Okay. Having set this last term to 0, now minimizing is rather easy. So I have to take this first fourth term and then I have to minimize with respect to psi mod square. So I will get alpha plus beta psi mod square plus half of m star vs square equal to 0. So that means psi mod square will become minus alpha by beta 1 plus m star vs square by twice alpha. Okay. Now I know that what is this quantity here? Who remembers alpha by beta? Does this ring a bell?
Density, NS.
NS.
Minus alpha by beta, because remember alpha is A T minus Tc. So in the superconducting state below Tc, alpha is negative. So minus alpha by beta is ns, or in other words, it is psi infinity mod square. So that is that is nothing but the superfluid density. And then here I can write this as I can write it in this form so that I have all positive parameters here. All right. So now Js, the supercurrent density, you know that it is psi mod square into E star. E star I can write it as twice V and Vs. So therefore I put the psi mod square from here, and what I get is twice E ns into 1 minus Vs square by twice alpha into Vs. Now you can immediately see that this function is a multi-valued function. First of all, so if I plot Js as a function of Vs, what is going to happen at low Vs? This term will not contribute much, and Vs is small, Vs square will be much, much smaller. So therefore, this term Vs will dominate. So initially I will have almost linear increase, but once this term starts contributing, this will start reducing this whole quantity. So therefore, it will go like this and it will fall to 0. So now this maximum, you can see that this has a maxima, and this maximum corresponds to the maximum current I can pass through the wire. In other words, this maximum current is the critical current. Now, this maximum you can you can take the derivative and find the maxima of this function. This is rather trivial, so I will leave this for you to do. But this value is where half m star Vs square equal to alpha by 3. Okay, so just minimize this function and or rather maximize this function, find where the derivative is 0 and you will get this. Okay, that it will be cube, you can immediately figure out from the fact that you have, when you differentiate this with respect to Vs, this quantity from the first term will give you 1 and this is a cubic term, so there will be a 3 that will come out, and therefore this is rather elementary. Okay, so then I can plug this in and find the critical current. And the critical current will be twice E ns into 2 by 3 into twice alpha by 3 m star to the power half. Okay, this doesn't help me much because it's a nasty expression. Means, what do I do with this? The point is, if you have started doing your assignment that you have to submit tomorrow, then you know what alpha is. And if you know what alpha is, then alpha is minus twice e square by mc square hc square lambda square. So you can use that, and then you get this whole thing in terms of more tractable quantities. So this becomes C HC divided by 3 into root 6 into pi into lambda. So these two are temperature dependent quantity, and if you know the temperature dependence of Hc and lambda, then you know the temperature dependence of Jc. But that is not the important point. The important point is, now let us try to compare this with a simplistic estimate, and the simplistic estimate is just by equating the kinetic energy to the condensation energy. Can you tell me what you get? Equate kinetic energy to condensation energy. See, when the kinetic energy is larger than the condensation energy, then of course the superconductor should get excited to the normal state. That is common sense. So, can anyone tell me what critical current I will get from that estimate? Okay, even if you don't get that, can someone tell me how to get it? What is the principle? What will I equate to what?
We'll get a velocity from this equation, and then try to multiply it with the density of electron.
Okay, the kinetic energy expression is what we have already what we are dealing with. So it is half ns m vs. So vs square. But if I am at the critical velocity, at the critical current, this will be Vc. So Vc is the velocity corresponding to Jc. Alright, so I will equate these to what? This is the kinetic energy, and if I have to equate this with the condensation energy, so that is h squared by 8 pi.
Yeah.
Alright? Now it is trivial. Put the expression of ns here, and what you will get is 2 pi by c square lambda square, and then you convert this Vc to Jc by using Jc equal to ns e Vc. So this is what you get here, and that is equal to 8c square by 8 pi. So this would give you a Jc value which is C 8c by 4 pi lambda. Now look at this and look at this. So we are not very bad. So this is the good estimate and this is the two-line estimate. The two-line estimate is not bad. It is capturing correctly the dependence on critical field on penetration depth. So it is C 8c by lambda, that part is okay. Prefactor has a problem, and the prefactor, what is happening is that GL estimate is smaller, and smaller by roughly a factor of 2. Factor of, to be precise, 3 root 6 by 4, and this is of the order of 1.8, so roughly 2. So we are getting the simplistic estimate is larger than the GL estimate by roughly a factor of 2. Can anyone guess physically why this simplistic estimate is larger? Why is the simplistic estimate larger than the GL estimate?
Yeah, in the simplistic estimate, we are only bothered about the kinetic energy of the superconducting electrons, but there is no interaction is included there. So the velocity will decrease due to the interaction, because the lambda square or the lambda to the power 4 represent an interaction, right? So that may cause the velocity in the yeah.
That represents an interaction. Okay, this is very complicated for me. I don't know how it represents an interaction. It represents, of course, it represents something, but an interaction, okay, I'm not very sure. But a simpler explanation, a more down to earth explanation that you can explain your, let's say that you can explain your brother who is reading higher secondary. Look, to understand what is happening, you have to think of the problem physically. When you are passing a current, what's happening is that the current is also suppressing the order parameter. So the order parameter is here, what you are assuming is that ns, which is actually ns is nothing but the chi mod square approximately. So you are assuming that Ns is remaining constant, but the order parameter is actually reducing also as you increase the current. So as you increase the current, it becomes, you don't have to excite by the whole condensation energy. You have to excite by a smaller energy. So this nonlinear effect is not incorporated here. That the current itself is also suppressing the order parameter. That is why you are overestimating. All right. This is one part. Now, but let us keep doing various, let us keep on playing with this expression. I sort of like this expression. So we also know, let me write this now in a different fashion. Not the simplified expression, we will go back to the full-fledged Ginzburg-Landau expression. I also know that the Ginzburg-Landau coherence length square is given by h cross square divided by twice m star alpha. Now this is something that you are supposed to show me that this quantity actually at zero temperature becomes the BCS coherence length. Maybe you all have already done it. Okay, so 1 by lambda, 1 by alpha modulus is twice m star Ginzburg-Landau coherence length square chi square xi square by h cross square. Okay, let me take again the expression for JC, which is twice E NS two by three into twice that's the expression here. Two by three m star into h mod square by twice of m star. Then there is a root over here. Sorry, I missed it. Xi mod square root. So therefore, now if I do my maths correctly, I will get twice E NS H star, H bar into 2 by 3 to the power 3 by 2 divided by, that's the reason I am being careful with these numbers, because there is a point that I want to make with these numbers. This I here. Now I can remove this 2 here and put n here. Okay. The reason I am writing in this form is so that you can compare now with the critical current that we had for a Josephson junction of the same size. So the critical current density for a Josephson junction weak link that we derived in the last class was EH cross NS, this part is the same, and divided by M into L. What was L? It was the length of the link. So now you can see that this critical current is actually larger than this critical current by a factor which is, so first of all, the weak link critical current is larger than the wire critical current by a factor that is not so important a factor, but here I have this factor which is psi by L. And remember here the assumption was that L is much smaller than psi. So in this case, you could imagine that this is actually these two large superconductor 1 and 2 connected by this small wire here. And then the critical current of the wire, if this was just a wire, should have been exactly same as what we have derived here. But it is not the case, because in the case of a Josephson junction, these two large reservoirs, they provide a robustness on this weak link, and because of that, the critical current of the Josephson junction is larger than the critical current of the wire. All right, so I think we will stop a little early today. There is just one thing more that I want to tell you, and that's the following. So this is something I want you to go back and compare. Recall the Cooper pair problem and Cooper's derivation of the pairing. Now you remember we had done something there, which is that we had assumed capital Q to be 0, which meant that The center of mass momentum we had assumed this to be 0. Now suppose you remove this constraint and you calculate again the binding energy of the Cooper pair. What you will realize is that at some critical value QC, the binding energy of the pair will vanish. Now this is the third critical current that you can derive from microscopic theory. So this is critical current derivation from the microscopic theory. So I would like all of you to go back, look at Ketterson's song or derive it yourself, and try to estimate how this critical current compares with the critical current that we have now derived for Ginzburg-Landau theory. Okay, so I think we'll stop here today, and it's on the eve of Diwali, so happy Diwali for everyone. And anyway, let me take questions.
Sir, it's something about the assignment that the thing that you have in the second question, that at the low temperature, the Ginsburg-Landau coherence length becomes the BCS coherence length.
Yes.
But but I'm not getting the factor exactly equals to 1. It's like 0.9 or something.
Yeah, that's right. There's nothing wrong. Look, the problem is that the BCS coherence length, if you do the various kinds of derivation, you have already seen that there is always a factor of the order of unity which is slightly different.
Yeah. The prefactor of H cut VF.
Exactly. It doesn't, but that doesn't matter, because you see, the problem is that how do you estimate the coherence length? Now, you know the coherence length from any experiment that you may estimate is not very precise. It's precise only within a factor of the order of unity. So, for any physical phenomena, the exact value of the BCS coherence length is not of any particular significance. All right?
Okay, sir. Okay. And sir, in the last question that you have given, the magnetic field, the Josephson junction under the application of a magnetic field.
Yeah.
But I can't understand exactly the geometry. The magnetic field is applied where? That is across the cross section of the junction.
Yes, you can
Weakly.
apply. You can apply it across the cross section of the junction, but you don't need to make any assumption of how the magnetic field is applied. That's a second order problem. So initially you just assume that there is a magnetic field, and that magnetic field is given by a vector potential. I think if you just take this assumption, and you can take the vector potential in the London gauge, that will make your life much easier.
Okay.
As long as you are working within this assumption, it should be fine. you'll get the same expression every time.
Okay, sir. Okay.
Okay. Physically, how you apply the magnetic field, of course, will determine how the Josephson junction will behave. The Josephson junction will behave very differently if you put the magnetic field perpendicular to the junction or along the junction. But those are when you solve the Josephson junction equation. I am just telling you to set up the Josephson junction equation. When you solve it, you have to be careful on which direction, how you are applying the field, not when setting it up.
Okay, sir. Okay, fine.
All right. Any other question? Okay. If not, see you again on Monday. We'll do little parts effect on Monday and then go over to full-fledged Josephson junctions. So, on real Josephson junctions and how to deal with them and how one can uh, derive their properties and make use of these properties. Okay, so let me sign out. Happy Diwali again and see you on Monday. Acha, Amit, are you still here?
Yes, sir. Yes, sir.
Now so I didn't notice this before. You wrote something problem occurring in audio. When was that?
Oh, it was when the mic of Obro was that was not muted.
I see. Oh, I see. Okay. All right.